Okay, this is a continuation, just kind of a finish up of the lecture 10 that I began on Monday for the course. And I'm going to talk to you specifically about doing something we're going to call normal depth computations. Let me back up here and get the crayon going here. Sorry about that. So we're going to look at what I'm going to call normal depth computations. And that is when you have uniform flow. And just to remind you, the uniform flow situation is when the velocity or any of the other parameters like depth do not change spatially as we move downstream. If that is the case, we can prove, looking at this flow regime here, if the velocity head and the depth don't change at section 1 to 2, we know that basically the slope of this energy grade line right here, that S sub F, is got to be equal to the bed slope here. And so we can say that the friction slope is equal to the bed slope. Now, a couple concepts that we covered in this particular lecture 10 was that the bed shear stress was equal to the unit weight of the fluid, the hydraulic radius. Remember that the hydraulic radius is equal to area divided by the wetted perimeter. And then the friction slope, if we know that S sub F is equal to S sub O in this particular uniform flow application, we can plug S sub O in for S sub F. Those are interchangeable. And we know that the shear stress can be approximated at that particular location for uniform flow depth as unit weight times hydraulic radius times the bed slope. Now we're going to set this one aside for the remainder of this lecture, and we're going to concentrate on the Manning equation right here. This is the Manning equation, which was derived earlier in this particular lecture, and that basically says that the velocity, the mean velocity of the channel, is equal to 1.49 over the roughness value N times the hydraulic radius to the 2/3 power times the friction slope to the 1/2 power. And if I have uniform flow conditions, I can plug in for the friction slope, I can substitute in the bed slope. Now, reminding you, this is the English version. Up here is the English version of the Manning equation. If you're going to be in SI units, where this would be in meters per second and the hydraulic radius would be in meters, that this coefficient, or the constant here on the top, is 1 instead of the 1.49, which you find in the English version. So if we have uniform flow, we can assume that the bed slope is equal to friction slope, and that's going to be very useful to us because we're going to today learn how to calculate the depth that would correspond to the uniform flow situation. We're going to call that the normal depth. And that's going to be useful to be able to characterize the regime of flow and help us in our water surface profile computations, because whenever water is flowing down a channel, it would love to go to the uniform flow depth. It's going to try to get there. It's rarely ever attained because it's a kind of a hypothetical or theoretical situation. There's always obstructions, there's always disturbances to the flow that's going to keep it from getting to uniform flow. But from that premise that we know that water normally wants to go to uniform flow conditions, we can use that to our advantage to be able to predict, kind of without doing that first computation, we kind of can predict what that water surface profile shape is going to look like, and it helps us to be able to judge our computational values later on. If we look at an example, and this is going to be an example of calculating the normal depth for a trapezoidal channel, we're going to be given a value of the Q, we're going to be given a value of the roughness, and we're going to know something about the bed slope. Okay, and so in this particular situation, we've got a trapezoidal channel right here, and we're going to want to calculate what the normal depth is, and sometimes I abbreviate that YN. You'll see it sometimes Y0. You may see that DN, just to know that this is considered the uniform flow depth or the normal depth. We're going to call that the normal depth. Now, if you recall several slides back, I had given you a table out of Chow's 1959 Open Channel Hydraulics textbook, which I learned my graduate course in open channel hydraulics is from there. I still use that textbook quite a bit today. If you can snag a copy ever, they're no longer in print. They're very expensive to buy on the open market, but if you ever see one at a book sale or something and you can get it fairly cheap, snag it up, because you can always sell it if nothing else for about $300 or $400. They're very expensive textbooks. But the main issue here is you're given a theoretical, or a standard shape of the cross section, and we have equations for the area, the wetted perimeter, the hydraulic radius, the top width, the hydraulic depth, which the hydraulic depth is equal to the area divided by the top width. Again, the hydraulic radius is the area divided by the wetted perimeter. And so for a trapezoidal channel, you've got some width here at the bottom, and then you've got these sloped sides, which they're going to be characterized by the horizontal to vertical component. So it's 2 to 1 side slopes. That would be the z is equal to 2, would mean that it's 2 horizontal to 1 vertical. And that's a little different than, we traditionally think of slope where we would have the rise over the run. Here we express it as the run to rise ratio. So if we've got a known bottom width, we know what the z is, that's 2. We can calculate the area if we know the depth. So the area would be the width at the bottom plus 2 times the y, and then that quantity to the depth of y. And then for wetted perimeter, we've got the equation, area divided by the wetted perimeter, that's the equation, and so on and so forth. If you had a rectangular channel, area is b times y, wetted perimeter is that. And so you just need to be familiar with this table, and you'll use it later on in the various types of problems, such as what you'll have for this lecture 10. Now, we're after the uniform flow depth. We're given that the discharge of the channel is 4,000 CFS. The bed slope is 0.002, and if we assume that that's uniform flow, that's also equal to friction slope, and the roughness value is 0.013. Now, for each this trapezoid channel, the equations for the area, wetted perimeter, and the hydraulic radius are here. And we can start plugging some things into the Manning equation, because remember, we're going to use the bed slope as the friction slope, so that's 0.002. In value here is 0.013. The flow rate here is going to be 4,000, but I'm not going to plug that in yet, and you'll see why in just a second. If I reduce this, I get an equation of 5.13 times the area times the hydraulic radius to 2/3 is equal to flow rate. We're going to actually plug in various values. We're going to do a trial and error method. There's other methods. You can use solver on your calculator. There's a Newton-Raphson method that the book teaches, and if you'd like to talk about it, I can go over that with you individually, or we can do it in study session or something like that. I can show you how that works. But we're going to use the brute force trial and error method, because even without a sophisticated calculator, you can do it this way. So let's copy down here in the next slide. The Q is equal to 5.13 AR to the 2/3. So let's just put that there, 5.13 AR to the 2/3. And I'm going to basically guess a value for the depth. And then I'm going to calculate the area, the wetted perimeter, hydraulic radius, and then I'll take it to 2/3 power. And then ultimately from this equation here, I'm going to calculate the Q. If the Q that I calculate matches my 4,000 CFS, then I'm done. And I've guessed correctly, and that's going to be the value for the normal depth. So I plug in the 6. I get from my equations over here, area 10D plus 2D squared. I'm going to plug in and get that's 132 square feet. Wetted perimeter, 36.83. Again, I'm getting that from the wetted perimeter equation here. Okay, that's from that table. And then the area divided by the wetted perimeter, 3.58, the 2/3 power, 2.34. I plug it in here to my equation up top, and I get 1585. That's not enough. I'm looking for 4,000 CFS, so I need to make another guess. I guess 8 feet of depth. I get 2925, still not big enough. I go down here, 9.2. I get 3973, almost there. 9.3, I'm at 4,068. So I know that it's somewhere between 9.2 and 9.3. I could step through it 100th at a time, 9.21, 9.22, etc., and look for 4,000. But I'm simply going to interpolate between the two and say that the normal depth is equal to 9.23 feet. All right, and so that's basically the way that you solve these kinds of problems, looking for the normal depth. What I'd like you to do now is go through the lecture 10 problems, the assignment, and make sure you can work those. And then on Monday, I'll take any questions you've got before we move on to a lecture 11. That concludes this lecture, so I want you now to work the lecture 10 assignment.